Yes, good morning. So in the previous videos, we have discussed about the problems on the firing circuits. So we have solved some of the problems related to R firing, RC firing, and RC half and full wave firing circuits we discussed. In this session, we'll discuss about another firing circuits, that is a unijunction transistor. So we have, as I said in the previous earlier videos, we have three different types of firing circuits, mainly R firing, RC firing, and UGAT firing. So it's the third important types of firing circuits which we are using. So it is unijunction transistors. So the drawbacks of R firing circuits. So unijunction transistor is nothing but the drawbacks of R firing and the RC firing is that the power dissipation in the gate circuit is more. So the drawbacks of these two is R and RC is the power dissipation in the gate circuit is more. Okay, to overcome this drawback, UJT firing circuit is used. Okay, so UJT is an observation for the unijunction transistor which was made up to N type of silicon material. Okay, with the P type of emitter is fixed. So it's made with the N type of silicon material with P type of emitter which is fixed. So UJT has a three terminals, has namely so emitter, base 1 and base 2. Okay, so B1 and B2. UJT has a three terminal, emitter, base 1 and base 2 here. See, this is the symbolic representation. You can there are a symbolic representation of unijunction transistor or UJT, so which consisting of a emitter, base 1, base 2 here. Okay, so in the structural view, so this is a cross sectional view of your BJT. So it consisting of a N type of semiconductor, P type of semiconductor, they are doped together. So P type of semiconductor will forms the emitter terminal of your BJT, UJT, and this N type of semiconductor will forms the base, base 1 and base 2 of the your unijunction transistor. It's a three terminal device consisting of base 1, base 2 and emitter. Okay, these are the three terminals of your BJT. So this is the structure or the cross sectional view of your unijunction transistor, and this is your equivalent circuit or schematic representation of a unijunction transistors. Okay, which consisting of the internal resistance RB1, RB2, then the diodes VB and VBB. So these are the equivalent circuit of your unijunction transistor. So this is a symbolic representation, this is a cross sectional view, and this is the equivalent circuit of your unijunction transistor. Okay, here RB1 and RB2 are the internal resistance respectively from the base 1 and base 2. So RB1 and RB2 are the internal resistances from base 1 and base 2 respectively. Then whenever the voltage VBB, just refer to the equivalent circuit here. So whenever the voltage VBB, so this VBB is applied, okay, so across the two base terminals B1 and B2, the potential at the point X with respect to B1 is given by, so this is your X point, so this is your X point whenever the VBB is applied between B2 and B1. So if you apply B2 between B2 and B1, if you apply the VBB, so then the potential at this voltage is given as Vx is equal to, Vx is nothing but the voltage at the X point, so it's I into RB1. So I is equal to, using the voltage divider rule, you can just calculate I is equal to VB divided by RB1 plus RB2 into RB1. You will get the Vx, the potential at the V. That means, so this is once again same, so RB1 divided by RB1 plus RB2 into VBB. So it is the Vx is equal to this one, this is the symbol which will indicate the efficiency UJT ratio. So it is represented as UJT ratio. So that is RB1 divided by RB1 plus RB2 is called as a UJT ratio. So Vx is equal to ratio into VBB. So where ratio this is RB1 divided by RB1 plus RB2. So RBB is RB1 plus RB2. So sum of RBB is nothing but it's a sum of RB1 plus RB2, the resistance at the base 1 and the resistance at the base 2. Okay, so where this one, the symbol efficiency type symbol, which will be the internal UJT voltage divider ratio, and it is called as the intrinsic standoff ratio, or this is the or voltage divider ratio of a unijunction transistor. It can also be called as a intrinsic standoff ratio, or it is also called as a UGT, voltage divider ratio. Okay, so this is about your UGT. So this is the characteristics for VBB and VBB for 0 and VBB for 15. So this is the characteristics, you can say VI characteristics of your this one. So your unijunction transistor. So this is for a VBB when it is 0, VBB when it is 15. So here two characteristics are shown here. So whatever this is whenever VBB is 0, and this characteristics is whenever VBB is 15 volts. Okay, so you can, this characteristics is divided into three regions. So cutoff region, the negative resistance region, and the saturation region. The characteristics of this unijunction transistor or UJT is divided as three regions, namely so cutoff region, the negative region, negative resistance region, and the saturation regions. So what exactly your cutoff region, what exactly happens in cutoff region, what exactly happens in negative region, and what exactly happens in the saturation region, we will discuss now. So this characteristics, the entire characteristics of unijunction transistor is divided into three different stages or the regions. So first one is cutoff region. We'll discuss what exactly happens in case of cutoff regions. So what happens here, whenever the emitter voltage VE which is less than VP, that means, so see here VE and less than VP, you can just refer to the equivalent circuit. So emitter voltage which is less than the phase voltage. So what happens in that case, just a minute. So whenever the emitter voltage V is less than VP, then the PN junction is reverse biased. So the PN junction is reverse biased, and the small amount of current, okay, of a reverse saturation current flows through the device. Very small amount of the current will be flowing. So you see here, see cutoff region. So cutoff, this up to here is cutoff region. So it's a current is negative. So whenever that is happens, so very small amount of current will be flowing. So very small amount of current will flows in that cutoff region. So through that device. Okay, so the negative resistance region. So when what happens here, when the emitter voltage V is becomes equal to VP, emitter voltage becomes phase voltage, then PN junction becomes a forward bias. So in this case what happens, the PN junction is reverse biased in the cutoff region. The PN junction is reverse biased, whereas negative resistance region, the PN junction is forward biased and IE starts flowing. That means the current flowing through the emitter, which will, I mean the through emitter there is a current starts flowing. The voltage across the device decreases in this region. So what happens, so voltage across the device, across the switch, these are all UJT, these are all the switches. So the voltage across that switch is reduces, okay, or decreases in this negative resistance region. So through the current passing, though the current is through the device is increases, hence the your voltage is reduces here. The voltage across the device is reduced, but the current, current is increases. Okay, though the voltage is reduced, the current is increases. So hence this reason, whatever the reason of operation of this UJT is called as a negative resistance reason. So your voltage is reducing, but the current is increasing here. So it is a hence the reason of operation is called as a negative resistance reason. So this decrease in resistance RB1, this reason is continued to till the valley point. So you can see here valley point is nothing but this negative reason, whatever happens. So from here to here, so they see here voltage is reducing in this case, so it will continue to this valley point. So the valley point is nothing but, so the point at which the saturation region, the point at which the switch goes to saturation, so that is called as a valley point. So this negative resistance region will persist from cutoff here to this valley point. Okay, the valley point is nothing but the point at which the saturation, the switch goes to the saturation mode, that's called as a valley point. Okay, here this region is continued to till the valley point. That's then after that valley point, the saturation, the switch or the device goes to the saturation mode. So saturation region, what happens, so further there is an increase in the IE value. So the emitter current further it will increases, so beyond the valley point. So beyond the valley point also, that is the beyond that drop down valley point or a drop down point, we can say. So beyond this also the current will be increases, then it drives the devices into the saturation region. So the further whatever the emitter current which will beyond the value point also it will increases, so thus the device will drives to the saturation region. So the voltage corresponding to this value point is called as a value point voltage, and it is denoted as VV. Okay, so above after value point also the emitter current is continue to increases. So because of this emitter current, so that your device will move to the saturation mode of operation. Okay, so the voltage at that particular value point is called as a value point voltage, and it is denoted as VV. Value point voltage is VV. Okay, the point at which this happened, it's called as a valley point. Okay, so these are the three three modes of three reasons of operations of UniJunction transistors. Okay, so next is UniJunction relaxation oscillator, that is UJT relaxation oscillator. The questions here, there are some of the few of the expected questions like with the relevant circuit diagram and waveforms, explain the UJT relaxation oscillator, or you may get the working principle of UJT relaxation oscillator with the help of the circuit diagram, and also show the period of oscillations, that is T is equal to RC log of 1 divided by 1 by 1 minus n. So this is the your UJT relaxation oscillator equivalent circuit, and this is a relevant waveform here. So what happens, so you have here your rectifier circuits you are having here. Okay, so this rectifier circuit will rectify and pass this voltage. So whenever the voltage will flowing through this resistance, the your variable resistance, then through the capacitance, so your capacitance starts charging. So this is the capacitance charge rising, charging is happens. So once the capacitor charges to its maximum peak value, so your gate receives the pulse here. So gate receives the pulse, so this will the pulse which is generated. So rapid charging and discharging, so there is a small pulse will be generating. So capacitor, because of the supply voltage, your capacitor is charging rapidly and discharging. So this process will continue. So while during the rapid charging and discharging, so there is a peak voltages, peak pulses are produced. Okay, so that peak pulses are used to trigger the gate. Okay, they are used to trigger the gate. So see here, so this is your charging period, discharging period, charging, sharp charging, we can say the sharp charging and discharging which will takes place in case of this UJT, so which will lead to produce the output pulses, the sharp pulses. So those pulses are used to trigger your SCR. So you can see, observe here, so this is a charging and discharging voltage, and this is a pulse which are produced here. So charging, so this is charging period, discharging period, charging period, discharging. Just if you cut down this, you will be getting the pulses like this. So these pulses are used for SCR turn on. So here you can see, so T off, that means T on, that means here is a charging, whatever the pulse is generated, that's called as considered as T on. That's if you, it's a duty cycle, T on plus T off. Duty cycle is T on plus T off, that is duty cycle is equal to T on divided by T on plus T off. So total time is T off plus T on. So duty cycle or duty ratio of this pulse generated is T on divided, it's a ratio of on time divided by the total time of the conduction. So this is about the UniJunction transistor, UJT relaxation oscillator. So let me explain a bit about this. So we know that the UJT relaxation oscillator, the circuit is shown here. So this equivalent circuit and the relevant waveforms are shown here. Okay, just refer to that. So whenever the DC supply voltage VBB which is applied across the capacitor, so if you apply the capacitor across the capacitor, so the capacitor begins to charges through the resistance exponentially. So there is a variable resistance is there. So from that variable resistance, the capacitor which starts charging exponentially towards VBB. So during this, what happens, this charging, the emitter circuit and the UJT is open circuited because of during this charging of this capacitor. So the emitter as well as UJT, they are open circuited. So the control voltage which is given by, so control voltage during this charging of capacitor is given by VC is equal to VC, that is equal to VE, that is a capacitor voltage which is equal to the emitter voltage which is given by VC is equal to VE, that is equal to VE that's equal to VBB into bracket of 1 minus of e raised to minus t divided by RC. Using this you can calculate the capacity, capacitor voltage or the emitter voltage of the UGAT relaxation oscillator. The charging time constant is given by T tau 1, it is denoted as tau 1, and it is the charging time, it is the product of resistance value and the capacitance which were used. So when this emitter voltage VE, which is equal to VC, so when this VE is becomes equal to VC, that means that reaches the peak point. So whenever the charging of this capacitor it reaches to its peak point, then the emitter voltage and the capacitor voltage becomes equal. So in that case, the discharging time constant, which is given by tau 2. So charging time is tau 1, it is denoted as tau 1. So the discharging time is tau 2, that is R1 into C1. So where the tau 2 is much smaller than tau 1, that is charging time is much smaller, discharging time is much smaller than the charging time. So you can see this is a charging time and this is a discharging time. So you can observe here just to in the waveforms here. So the time taken to charge, so this much is the charging time, only this much is the discharging time. So that is what I am telling here. So here always the charging time is higher and the discharging time is very less. Okay, so the different parameters, when the discharging voltage is dropped to, that is your valley point VV, so the UJT turns off, then the charging and discharging process of the capacitor repeats. So when discharging voltage dropped below the valley voltage, then what happens, UJT turns off, the charging and discharging process, and the capacitor repeats for each period of t here, so which is given by t is equal to RC into bracket of ln of, so 1 divided by 1 minus n, 1 minus this one efficiency symbol, which is your ratio. Okay, so R2 is used for the thermal stability of VP, and the R2 is calculated by using the formula. So this is the formula, you can calculate the value of R2 here. It is 10⁴ into the ratio and to VB. So VB is not efficiency, it's a ratio. So then the maximum value of R is determined by R max is equal to your VBB minus VP, so divided by IP. So VP is this one ratio into VBB plus VT divided by IP. So the minimum value of R is given by R minimum is equal to VBB minus VBB is nothing but the voltage which is applied across between two bases, B1 and base 1 and base 2. VV is nothing but it is the valley point voltage. So valley point voltage divided by current at the valley point. So IV is nothing but the current at valley point, and VV is nothing but the voltage at the valley point. So using that you can calculate the minimum value of the resistance. So then R1 is calculated using this formula. Just refer to this formula. Just using this you can calculate the value of R1. Okay, so these are the different listing of formulas. Just you have to remember these are the formulas. So list of formulas given. So how these formulas are came, we have already discussed here. So I have listed out some of the formulas which are very much helpful when solving the problems related to UGAT relaxation oscillator. So the capacitor voltage formula, then the charging time, discharging time. Okay, then other formulas are listed here. So UGAT relaxation oscillator formula list. So this list will be definitely helpful in solving the problems related to UGT relaxation oscillator. Just go through these formulas, just understand how these formulas are arrived. Okay, just recall this, keep it remember, so that in the next session we'll discuss about the problems on this UGT relaxation oscillator. These around 11 formulas I have listed out here. So just keep an eye on these 11 formulas. Okay, so while solving the problems related to UGT relaxation oscillator, all these 11 formulas are helpful. Okay, so if you got any doubts here in this UGT relaxation oscillator, just contact me here to clarify your doubts. Okay, so before that, so to solve the problems on this, so these formulas are very much essential. Just go through those all formulas and be ready. Well, in the next video we'll discuss about the problems on UGT relaxation oscillator. Okay, till then if you got any doubts you can feel free to contact me anytime. Okay, thank you.